Good afternoon. This file contains the pre-lecture notes for class on Tuesday, October 15th, 2013. The relevant reading is the first half of the Carey chapter, 8.1 through 8.8. This week we continue our discussion of substitution reactions. Specifically in this pre-lecture, we'll talk exclusively about SN2 reactions and the factors that affect SN2 mechanisms. On that note, we will explore the idea of nucleophilicity. You already know what a nucleophile is. A nucleophile is an electron-rich species that can attack an electrophile. In this pre-lecture, we'll talk about the different factors that affect the strength of a nucleophile. So how can we determine what is a good nucleophile versus what is a bad nucleophile? We'll also continue our discussion of Sovalis' reactions, which we've talked about with regard to eliminations, but here we'll apply it to substitution reactions. Substitution Sovalis reactions are any substitution reactions in which the solvent acts as a nucleophile. So, to recap from last week, remember the characteristics of the SN2 mechanism. It's a bimolecular mechanism that depends on the concentration both of your starting material, whether it's an alcohol or an alkyl halide, here as I've indicated in the rate law, Rx, and also on the concentration of your nucleophile. It has a concerted mechanism. There are no intermediates. If an alcohol is involved, you have a preliminary step that involves the protonation of the alcohol, but the SN2 step itself does not involve any intermediates. Also remember that the reaction is stereospecific, which means that we get one specific stereoisomer out of the reaction if we start with a stereoisomer in our starting materials. For the SN2 mechanism, we always produce a stereochemical inversion in Rx such that whatever the stereoisomer you began with, you get its enantiomer out or its diastereomer, depending on how many chiral centers there are. So, recall the generic mechanism for nucleophilic substitution via SN2. Here I have a generic nucleophile Y attacking the alpha carbon in an alkyl halide as the leaving group leaves from the alpha carbon. This gives us our new substitution product as well as an anion of the leaving group. In this case, our nucleophile is a Lewis base because it's donating an electron pair, and often throughout your textbook you'll see examples of nucleophiles that are anions. They're negatively charged and used with sodium ions or potassium ions as salts. Usually the substrate is an alkyl halide. We spent a lot of time last week talking about how to make alcohols undergo substitution. This week we'll focus mostly on the alkyl halides. Remember that SN2 mechanisms are stereospecific. Always the nucleophile must come in from the backside of the alpha carbon to eject the leaving group from the front side of the alpha carbon. This is known as backside attack. The consequence of backside attack is that we get stereochemical inversion at any chiral centers involved in an SN2 reaction. So here is a 3D model showing you an example of what this looks like. The nucleophile, in this case indicated with the blue sphere and a negative charge on it, approaches from the opposite side of the leaving group, indicated with the red sphere here in the molecular model. As the nucleophile bonds together with the alpha carbon, the leaving group leaves, producing a negative anion leaving group. Notice that we have a stereochemical inversion. All three of the atoms that are attached to the alpha carbon shift slightly in their spatial orientations, producing a stereoisomer of the starting material. In any case where the starting material is chiral, we produce its enantiomer or diastereomer, depending on how many chiral centers there are in the molecule, in the product. So for example, if we start with plus 2-bromooctane and we react it with hydroxide anion in an SN2 reaction, we produce minus 2-octanol. If we start with minus 2-bromooctane, we will produce plus 2-octanol. We get the opposite rotation of light due to stereochemical inversion. Here, using dash wedge perspective formulas, we can see how this works. Notice what happens in this case. The bromide leaving group in the starting material is here. Right? The product has the nucleophile OH group attached to the alpha carbon on the opposite side of where the leaving group was in the starting material. This causes S plus 2-bromooctane to convert to R minus 2-octanol after the stereochemical inversion step. So, what are some good nucleophiles that we use in SN2 reactions? Remember, the generic Y stands for the nucleophile in this case, and this can be any small molecule that is electron rich. So here at the bottom of the slide, I've given you 6 different examples of electrophiles that you might see. You could see alkoxide anions, thiol anions, cyanide, um, ester anions, azide anions, or even other halide anions. All are good nucleophiles. Remember, not all nucleophiles are anions. All of the nucleophiles we discussed on the previous slides were anions. Those included such things as hydroxide anion, thiol anion, alkoxide anions like methoxide, a cyanide anion. Students find it very easy to memorize that as long as they have an anion, they'll have an SN2 mechanism. This is not always the case. In many cases, we have nucleophiles that are quite good nucleophiles, but they're neutral. So consider here water, methanol, and ammonia are all very good examples of nucleophiles that are not negatively charged. All of these nucleophiles, however, are Lewis bases. We want to spend the bulk of this pre-lecture talking about the different factors that affect the rate of an SN2 reaction. There are 4 factors you have to consider when determining how quickly different reactions will take place under SN2 mechanisms. Those are: what is the nature of the leaving group? Is there any steric hindrance in the alkyl halide? How good a nucleophile is the nucleophile you're using for your SN2 reaction? What is its nucleophilicity? And lastly, the solvent structure. What's the solvent that you're using in order to produce a reaction? So first, let's consider leaving groups and the rate of an SN2 reaction. Increasing the stability of the leaving group always increases the rate of an SN2 reaction. This is exactly the same thing that we learned about with regard to E2 eliminations, right? Going down the periodic table from fluorine to iodine, we increase the reactivity of an SN2 mechanism. Chlorine, bromine, and iodine are all better leaving groups than fluorine. In fact, fluorine is such a terrible leaving group, it won't leave under any SN2 mechanisms, and it's not reactive at all. Iodine is the best leaving group, followed by bromine, followed by chlorine. So when comparing the different halogens one to another in the periodic table going down the family, you should be able to predict which one of these alkyl halides would react the fastest. As I've indicated on this slide, of course, this alkyl iodide would react faster than the bromide or the chloride. It's important to note that we may have more leaving groups than simply halogens. Although alkyl halides are the most common starting materials we'll work with when we're doing SN2 mechanisms, you may see incidences where you have other leaving groups than a halogen. The 2 most common ones that you'll see include the mesylate leaving group and the tosylate leaving group, which I've indicated on this slide. Mesylate refers to the leaving group that is composed of all of the atoms attached to the R alkyl group. Tosylate refers to all of the atoms in the leaving group attached to the R alkyl group, as you can see here. These are both great leaving groups, and we use them in specific reactions to convert alcohols to good leaving groups. Remember that alcohols are not good leaving groups by themselves. OH groups don't want to come off. We have to make them better leaving groups. Up until this point in the semester, you've always learned that the easiest way to convert an alcohol to a good leaving group is to use a strong acid to protonate it. These 2 leaving groups on this slide are used instead of acid in any conditions under which you don't want to have acids present in your reaction. How do you prepare mesylates and tosylates? Well, we prepare them pretty much in similar ways. You combine your alcohol together with the tosyl chloride under basic conditions, and this produces a new compound that has your tosylate leaving group on it. This now makes the alcohol a very good leaving group in much the same way that your acid protonation makes alcohols a good leaving group, and this compound can now undergo substitution reactions. In general, the best leaving groups are weakly basic. You should already have been able to anticipate that from the previous slide that showed you the relative rates of reaction of the different halogens going down the family of the periodic table. Remember, iodine is a much weaker base than fluorine because iodine is much more stable as its anion iodide. Hydrogen iodide is a very strong acid. As such, its conjugate base is very weak. Looking at a table of the relative rates of each of the leaving groups considered with the same alkyl substituent, you can see what we mean in terms of increasing rate of reaction as we move down the periodic table, considering all of the halogens together, as well as if we compare oxygen leaving groups to each other. Water reacts much slower than the tosylate anion leaving group, which reacts slower than the mesylate anion leaving group. Note the relative pKa's of all of these compounds as well. As we increase the relative rate of SN2 reaction, notice that the pKa of the conjugate acids go down. Lower conjugate acid pKa means stronger acids. This must mean that the leaving groups themselves, as we go down the list, are much, much weaker bases. The second factor that we'll consider is steric hindrance with regard to the SN2 mechanism. Steric hindrance refers, remember, to the crowding of atoms that are within a compound. Here, steric hindrance applies directly to the number of alkyl groups that are attached to the alpha carbon where our leaving group is located. The more alkyl groups that surround the alpha carbon where our leaving group is attached, the harder and harder it is for a nucleophile to approach the alpha carbon to kick out the leaving group. Think of all the alkyl substituents around the alpha carbon as in the way of the nucleophile. They're blocking the approach of the nucleophile. As such, we can see that with fewer alkyl groups around an alpha carbon, we increase the relative rate of an SN2 reaction. The fastest reaction would occur here in our homologous series with methyl bromide. Methyl bromide has no alkyl groups around its alpha carbon, so it reacts the fastest. It's easy for any nucleophile, in this case an iodide in our reaction that we're taking a look at, to approach this methyl group because there's no alkyl groups in the way. The rate slows down significantly when we consider primary alkyl substituted halides. Adding one methyl group slows this reaction down by several orders of magnitude. Adding another alkyl group, in this case isopropyl bromide, slows it down another several orders of magnitude. Finally, tertiary alkyl bromide, right, any tertiary alkyl halide, reacts so slowly that we don't get any substitution products out, and if we do, they're too small to measure. So, the takeaway is that increasing the amount of steric hindrance around your alpha carbon decreases the rate of SN2 reaction. Note that steric hindrance effects also apply to branching around the alpha carbon. On the previous slide, we looked at the relative rates of just adding single methyl groups to the alpha carbon. But note here, in the series that we're comparing on this slide, we're not adding more and more alkyl groups in long chains to our alpha carbon, but we are increasing the number of branches coming off the alkyl groups attached to the alpha carbon. The more branched the alkyl groups are around the alpha carbon, once again, the slower the relative rate. This is exactly the same effect that we were talking about on the previous slide. The more crowded alkyl groups are around the alpha carbon, the harder it is for a nucleophile to approach the backside of the alpha carbon, and it slows the relative rate down. If we look at the relative rates of reactions of both negatively charged anions and neutral nucleophiles, we can see that negatively charged nucleophiles react under SN2 mechanisms at much higher relative rates than neutral nucleophiles do. Right. Very good nucleophiles, such as iodide and thiol anions, react at much faster rates than good nucleophiles like halogen anions, such as bromide, hydroxide, alkoxide, cyanide, or azide anions. Right. The nucleophiles get relatively worse as we lose charge on them, so ammonia reacts at relatively the same rate as chloride, fluoride, and our carboxylate anion. Weak nucleophiles and very weak nucleophiles, you can see, are such things as solvents like water, an alcohol, or a carboxylic acid. these solvents carry no charge, and in fact, these solvents are acidic in nature, which makes them poor nucleophiles. This doesn't mean that they won't react under SN2 mechanisms, but it does mean that any SN2 mechanism that's possible with them is very slow compared to other nucleophiles. In general, nucleophilicity increases as the basicity of a compound increases. Okay? Basicity refers to the ability of a compound to act like a base. As electron density increases, okay, as electronegativity increases, the more electron rich a compound is, the better the nucleophile it is. So we can see here, going down comparing all of our oxygen compounds, our oxygen containing nucleophiles, the best oxygen containing nucleophiles are those that carry a negative charge on the oxygen anions. In this case, the carboxylate anion is a fair nucleophile because it's pretty stable as is due to the resonance structures contained therein, and our weakest nucleophiles are alcohols and water, which contain no negative charge. Remember, solvents themselves can react as nucleophiles. Okay? They are nucleophilic. They're not good nucleophiles, but they can act as nucleophiles in SN2 reactions. The final factor we'll consider with regard to determining the relative rate of an SN2 reaction concerns the solvent structure. In general, all organic reactions you'll learn in this class will occur in two types of solvents. Polar protic solvents, these are polar solvents that contain acidic protons in them, and polar aprotic solvents, these are polar solvents that do not contain any acidic protons in them. In general, SN2 reactions preferentially occur in polar aprotic solvents. Polar aprotic solvents prefer SN2 reactions. So when comparing the same reaction that occurs in two different solvents, you can speed up the relative rate of an SN2 reaction by placing it in a polar aprotic solvent. The reason for this is because polar aprotic solvents increase the nucleophilicity of the attacking base. Consider without the availability of acidic protons, you have very little hydrogen bonding between negatively charged nucleophiles and any protons that are in the solvent. That makes the nucleophile a much better nucleophile because it's not being taken up by hydrogen bonding to the solvent, and it's better available to attack the alpha carbon in your alkyl halide. Here on this table, we can see the relative rates of SN2 reactions that are occurring in different types of solvent. Right? The first two solvents, methanol and water, see that they're polar protic solvents. Both of these compounds are polar, and they both contain hydrogen atoms that are acidic. Okay. Down here, we have three polar aprotic solvents, dimethyl sulfoxide, dimethyl formamide, and acetonitrile. They don't contain any protic hydrogens. Look at how the reaction at the top, the substitution of bromide with an azide anion, increases as we move from the polar protic solvents to the polar aprotic solvents. The rates of reaction in all three of the polar aprotic solvents are orders of magnitude greater than they are in the polar protic solvents. Because solvents themselves can act as nucleophiles, don't forget that solvolysis reactions can occur in substitution mechanisms in the same way that you learned about them for elimination reactions. In this case, it simply means that the solvent itself is the nucleophile as well as the solvent that the reaction occurs in. So, up top we see an example of an alkyl halide combined together with the negatively charged anion to perform a substitution reaction where the nucleophile replaces the halide. In a solvolysis reaction, the nucleophile is going to be neutral because there's no negative charge carried on our solvent particles. In this case, after the substitution reaction occurs, you will have a protonated nucleophile that has a sigma bond to your alpha carbon in your original alkyl halide. Don't forget that in any case where you see something like this, the last step is to do what? To deprotonate the protonated nucleophile. You've seen this before when water acts as a nucleophile in previous weeks. You can simply use another water molecule to remove the proton from the protonated nucleophile in your product, thus giving you the product of the overall reaction to be RNU plus HX. Typical solvents that you will see used in solvolysis reactions pretty much include alcohol-containing compounds or OH-containing compounds. I've listed quite a few of them here. water, methanol, ethanol, formic acid, acetic acid. Don't get confused by the list of them, but note what's common in all of them. All of them have OH groups in them. All of them have OH groups in them. The lone pairs on this oxygen in the OH group is capable of acting like a nucleophile in a substitution reaction. On the right side, I've listed the prototypical products that would be produced from the reaction with any of these solvents and a generic alkyl halide RX. My intent with this slide is not for you to memorize what all of the products are from all of these different solvents, but for you to have an opportunity to see what those products would look like were you confronted with any of these different solvents in a typical solvolysis reaction. With that, this pre-lecture is concluded. Make sure that you review those relative sections in the textbook and come to class prepared to apply what you've learned.